Okay, creationism versus evolution. Somebody commented the other day about nothing does not prove creation. Actually, we're not looking at nothing, we're looking at something all around us. For example, cosmic radiation. What does that do to point to the controversy between creationism versus evolution? Seems to actually give a point of view that supports a recent young Earth creationism. Let's take a look at this up here, K53A. We have to put .htm on it. Where's my dot? There it is. And I'll click on this. And we have radioactivity age measurements continued. Methods of age measurement indicate a young Earth. We have external energy sources, and we're looking at cosmic radiation. Of particular interest in this connection are the intensely powerful cosmic rays. The character of these rays is indicated by the following. To begin with, primary cosmic radiation, that is, the rays as they exist in space, is composed of atomic nuclei traveling with speed so enormous as to approach that of light. The rays are mainly nuclei of atoms, of many of the chemical elements, especially in hydrogen and helium, but also including heavier elements. The energies of these particles are tremendous, ranging from 1 billion to over a billion electron volts, far beyond the capacities of our largest man-made accelerators, compared to the 27 million electron volt energy barrier in uranium atom. This tremendous energy of this radiation, as it enters the upper atmosphere and collides with air atoms, results in the formation of a secondary stream of charged particles in great variety. Before these particles, the primary cosmic radiation, can reach the Earth's surface, they must pass through the atmosphere. The blanket of air covering our planet is heavier than many realize, equivalent to a layer of water 34 feet thick. And this was even more substantial before the flood, when you had an ice canopy of water, and it was so cold that the hydrogen was metallic. So a lot of radiation from outside, the sun and outer space, did not get through. Even the tremendous energy of the primary cosmic rays is not sufficient to enable them to get through this much matter unchanged. This much matter of the blanket over the Earth, the air. However, the debris resulting from their collisions with air atoms does reach the surface of the Earth, and in fact has been detected several hundred feet underground. This debris, in addition to the protons and neutrons of which the struck atoms are composed, includes mesons and unstable particles associated with nuclear structure that are not very well understood at present, and gamma rays, like those given off by radium, only more penetrating in positive and negative electrons. So all of that is bombarding the Earth. Although comparatively little of the cosmic radiation actually reaches the Earth's surface at present, that part which does reach it gives intimation of the tremendous energy that certain of its particles contain. The extraordinary penetrating power of cosmic rays is shown, in the first place, by their ability to pass through the Earth's atmosphere, the absorptive power of which for ionizing radiations is approximately equivalent to 1 meter thickness of lead. But that is not all. The rays have been detected underground and underwater at distances equivalent to 1,400 meters of water below the Earth's surface. Only particles with many billions of electronic volts of energy could have penetrated to such depths. So it's out there. Samuel Gladstone. The portion of the cosmic radiation reaching the Earth's surface seems to consist predominantly of highly energetic mesons, along with some neutrons, electrons, protons, and photons. Mesons are particles mesons are particles intermediate in mass between electrons and protons, which decay very rapidly into electrons. Now the question arises as to what effects might be produced on the Earth's surface if a substantial portion of this hard component of the cosmic radiation, rather than only a very insignificant part, as we most note today, could reach the Earth. It does seem highly probable that such an environment, which must have reached the Earth's surface to at least some degree, both during the first day of the creation and during the deluge period, and possibly at other times as well, would have had a marked effect on such radioactive elements in particular. The bombardment of these atoms, which are basically unstable anyway, by large amounts of various kinds of particles of extremely high energy, could hardly fail to have added to their instability. Or to put it another way, the addition of large amounts of external energy into the atomic nucleus would have supplied the needed energy for alpha particles or other groups to overcome the energy barrier normally retaining most of them within the nucleus. This means that it is not only possible but highly probable that the disintegration rates of radioactive elements would have been much higher than at present during at least these two periods of Earth history. Interesting. And that Earth canopy of water fell down on the Earth in rain, all this radiation could come in. However, there seems to be no way on the basis of present knowledge by which the magnitude of this increase in rates can now be determined. So again, radiometric dating is not an exact science. You don't know what's happened in the past. The conclusions that the deluge occurred point towards the deluge. The water all over the planet, the destruction, the things that are catastrophic, determined, must have been a whole bunch of water throughout the planet, ice age, all these things indicate that, okay, then what about the radiation, like the cosmic radiation from the outside, the space? The postulated environment would probably produce a variety of nuclear transmutations in addition to accelerating the disintegration of uranium and thorium. Accelerated, so it makes it look a lot older. If it was multiplied, you'd have billions of years represented in moments of time, just short moments. The various elements in each decay chain would also be affected. It is thus not strictly correct to speak of a simple increase in decay rates as resulting from such an environment. However, the net effect is the same, namely an increase in the ratios of daughter to parent elements in each series. Just the time is a lot shorter. Now we have the Van Allen radiation belt. There may also have been other sources of radiation and energy during these periods. The mere fact that the quantity of actively radioactive material in the Earth must originally have been greater than at present would have been one such environmental factor. Also, one of the results of the artificial satellite studies in the higher atmosphere has been to reveal a belt of very high incidence of corpuscular radiation. The abnormal radiation was found above the level about 450 miles high. These radiation belts contain far more radiation than that due to the incidence of the cosmic rays. The many and diversified electrical and magnetic phenomena in and around the Earth's upper atmosphere are thus extremely interesting, but as yet little understood. Just how they all interact with each other at present, or how they may have acted in the past, is not known. It is plain, however, that there is an abundance of rays and charged particles of high energies which, if any substantial portion could reach the Earth's surface, would undoubtedly produce very significant changes in many geophysical processes and phenomena, certainly including those of radioactivity. A highly radioactive environment, such as postulated, may, in addition to accelerating the decay of certain elements, have formed artificial radioactive elements with various decay rates. The fact that these have not been found in nature may mean either that they just have been not yet found, or else that their initial decay rates were also higher than at present, and they have substantially vanished by now. It is only the elements with the very long half-lives that have survived the accelerated decay periods. So, without knowing what these accelerated decay periods have done, we can't be sure about measuring how old the Earth is by taking a sample of rock that has U-235 in it and measuring, and then going back to as if everything is the way we look at it and see it today. Uniformitarianism is not there. We conclude, therefore, that a time measurement based on the principle of radioactive decay is in itself quite inconclusive. It is in the first place quite reasonable to believe that both parent and daughter elements in each radioactive chain were created at the beginning, probably in equilibrium amounts. The amount of originally created radiogenic end product in each chain is uncertain. It is likely, however, that homologous amounts were created in all such minerals, so that all such elements would, when created, give an appearance of the same degree of maturity or of age. Appearance, but not actual age. Furthermore, the intense environmental radiation present in the upper atmosphere could well have resulted in much higher decay rates for the radioactive elements at one or more times in the past. So, thus, by the end of the creation period, each radioactive mineral would very likely contain a sizable amount of its radiogenic daughter, though actually but a few days old. Well, then you don't have the half-life. You had just a few days. Again, at the time of the deluge, it seems reasonable that the increased radioactivity in the environment would have speeded up all decay processes by the same unknown amount. Therefore, even in the relatively rare cases where the radioactive mineral was not disturbed excessively during the intense geologic upheavals of the creation and deluge periods, the relative amounts of parents and daughter elements would still be entirely incapable of yielding a valid record of true age, since neither the original amount of radiogenic material nor the changes in past decay rates can now be determined. The only thing reasonably certain is that the present decay rate and present amount of daughter element, if applied in a uniformitarian computation, must result in an age estimated immensely too great. A couple of days, and it looks like it's millions of years, because all you have to do is accelerate the radiation rate with outside external evidence of radiation, cosmic rays, and the other radiation that appears around 450 miles above the Earth. Lead age methods, defective methods and faulty interpretation causes erroneous results. Now we look at this, we've already concluded the unsubstantiated unreliability of radiometric dating, especially when it gets to be something like the lead age radiometric with uranium date methods. Consider, for example, the various methods based on disintegration of uranium and thorium into lead. Each of the parent elements disintegrates by some process through a certain chain of events and isotopes until it reaches a stable condition. Lead. Geochronological use of these facts requires very accurate measurements of the amounts of the various elements of the chain present in the mineral, and also very accurate knowledge of the respective decay constants. The techniques for these determinations are exceedingly difficult and subject to large error. Although radioactivity measurements of geologic age have been widely accepted for some 50 years and have been responsible for the wide acceptance of an age for the Earth measured in billions of years, it is now generally admitted that most of the work done before 1950 was quite misleading, mainly because of defective measurements or interpretations of the measurements. Gordon Gastill has recently reminded his colleagues, attempts to measure mineral age began soon after the discovery of natural fission. During each decade since then, analysts have discarded most of the age determinations made in the preceding one. Look in the Scientific American Journal of Science, the American Journal of Science here. So, original lead not considered in radioactive age determinations draws false conclusions. A more important reason for the errors in the earlier published ages